Thank you guys very much for attending our third quarter webinar for 2020. Today, I and Joe with Grout, we're going to be discussing Grout and Helical Pulldown Micropiles and hollow bar Micropiles. I'm going to be pretty topical with most of the content that I'm presenting, and this presentation is really just to serve as a reference material. Should give you a good idea when you're going through a design methodology of what the different parts and components are. So it's not going to be so in-depth that you'll be able to do a design, but you'll be able to look through the design methodology and see what's what and have a good understanding of what's going on. So this is the general outline for how the presentation should flow. I'm hoping to keep it within 55 minutes or so with a few minutes at the end for questions. I'm going to be co-presenting with Joe Schatz with Grout. Joe's going to cover grout principles and practice, and then after that, I'm going to be going over the installation and components for the helical pull-down micropiles and hollow bar micropiles. And then I'm going to talk about a little bit of design principles at the end, sort of things that we're checking with each design. So I'm going to start off by going through some brief introductions for who we are as a company and what we do. So here's the staff that you could be directly interfacing with to get your projects quoted or designed. First off is Tim Combs, who's our president. He's been in and around the industry for 25 years and has been he's very knowledgeable on industry things, a lot of unique things that have gone on that have happened that have been unique solutions. So he's a really good resource. So we'll skip him for now. We have our sales team, which consists of 4 primary individuals. They're the ones that are interfacing with our partners and getting quotes together and helping to manage a lot of the parts of the sale. So first off, Bill Sears is our National Director of Sales. He's also currently takes care of our lower Midwest region for sales. Luke Curley is our upper Midwest regional sales manager, and he's located up near Detroit. Jack Hawk is our Southeast Regional Sales Manager down in Atlanta, primarily focusing on the MagnaCore hollow bar as well as a few other things. Then we have Jim Sorrell at the bottom right. He's our national and international Hydroway sales rep. He's been here a long time and he's extremely knowledgeable of the product line. So if you have any questions about that, he's definitely a good resource. Additionally to, we're always looking to grow and expand our sales team. So if you have any contacts that, would be a good contact, please feel free to pass that along. So those are our sales guys. We have our engineering staff, which is currently Sam Pappas and myself, Sean Hibbets. We take care of the engineering quoting, design assistance during the design phase, like calculations, drawings, submittals, VE options, and also we can help during installation to troubleshoot. We look to be really creative and try to come up with unique, solutions when we're presented with design scenarios. So if you have any questions, feel free to bounce it off of us. So a little background on Sam. He's an EIT. He's also a bachelor's level engineer from SLU in St. Louis, looking to obtain his master's degree from SIU in the next few years and then also get his PE. I'm a master's level professional engineer in the state of Missouri. I've operated in capacities from consulting geotechnical engineering with a lot of different experience with deep foundation projects, different types of slopes and reinforcement and stuff like that. So I also did a short stint in the Army Corps of Engineers where I worked on levees, dams, and other government projects. So Sam and I head up our engineering staff, but we also retain the services of a handful of experienced geostructural engineers who are used to working with our elements. They cover a pretty broad portion of the country, and they help assist us with some turnkey engineering submittal packages. So if you have a design that you need to get a submittal done on, we can help you with that. So finally, but not least, Josh and Chris, our operations staff in St. Louis. Then we got James and Eddie and our operations staff up in Detroit. They take care of the orders when they're placed. They're making sure that everything's packed up right and tight, that everything's stocked that needs to be stocked. So they're the go-to guys for that. All right. So like I said kind of before, we have 2 locations for our warehouses. One's in Caseyville, Illinois, which is pretty much in St. Louis, and then Livonia, Michigan, which is pretty much in Detroit. So we ship out of those 2 places, and we can manage, to get your products at your project site. So as Intech, we represent these 5 brands as well as a few others, and these are the ones that we provide a wide array of engineering solutions to our partners. So first off, Chance and Atlas represents our line of helical anchors and resistance piers or push piers. We're one of a handful of Chance distributors representing a good portion of the middle of the country up through the Northeast, and I'll show you that in a minute. Chance is an extremely well-respected manufacturer with over 100 years in the industry. They carry a lot of the original patents on helicals and resistance piers. So then we have MagnaCore, which is our brand of hollow bar micropile. So it's a specific type of micropile installation, which I'll discuss more in depth later. But basically, it's a competitive option when you compare it with a cased conventional micropile. It's a great one-pass method of installation, and it's very effective in maintaining an open hole in collapsible soils, so you don't have to advance and withdraw casing to keep the hole open. So third is our Carbon Bond, which is our carbon fiber structural crack repair system. It's a composite resin carbon fiber reinforcing that provides tensile strength to existing structures. So it can increase the capacity of an existing structure or help repair it if it has undergone any cracking failures or anything like that. It's an effective way of, reducing the cost associated with changing the strengths or of an existing member or repairing it. And then finally, Hydroway is our geosynthetic wrapped strip drain product. It's an effective way of transmitting water through an underground pipe channel without the concern of having the soils move into the flow. So it has a high permeability and a high flow through rate, and it's a very cost-effective way of piping water underground. So I wanted to include my contact information, and I'll have Joe's as well. If you have any questions or comments about anything you see today, anything you'd like to see presented in the future, or need any design assistance, feel free to reach out to me and contact me at any point. So here's a graphic representation of our footprint with Chance helical piers and Atlas resistance piers. So like I said, we're a distributor. This is our territory where our partners are based. We have a lot of activity and experience in these areas with a lot of the local engineers and contractors. So then this image shows the footprint of where we market our hollow bar micropile MagnaCore. As you can see, we're not restricted to a territory in the United States. We can also offer it out of the United States. So if you have anything, any projects that you need design assistance or solutions for, feel free to reach out. And then finally, here's our Hydroway footprint. We currently sell and market this solution worldwide, so reach out to us if you have a need for that. So at this point, I'm going to turn it over to Joe with ChemGrout to present on grouting theory and practice. So feel free to take it away, Joe.
Okay, my name is Joe Schatz. I'm with ChemGrout. We're a manufacturer of mixing and pumping equipment for grout, and we have several machines for the application of anchors and micropiles. We're going to go through a little bit of the theory of cement, the water to cement ratios, and the quality control, and then we'll get into the actual practice of the equipment to use, the operations of how to use the equipment, and a little bit on the safety of the equipment. So let's start by going through the grout theory. First, the main raw material is cement. Cement is made from several different raw materials: limestone, shells or shale, clay, and iron. And then they grind and refine these materials, and they get the raw materials of calcium, silicon, aluminum, and iron, the raw materials that are used for cement. Once they have the raw materials, they're all combined into a furnace, and they're heated to a very high temperature, about 2600 Fahrenheit, and they're ground up into a fine clinker material that ends up being a ground material into cement. That's the gray powder that we're used to. Cement's available in several different types depending on the combinations of the raw materials they use. Type 1 and Type 2 are the normal raw materials. Type 2 cement is when you say Portland cement, most times they're referring to Type 2 cement, which has a moderate sulfite resistance. The other types of cement are high early cement, which has a quick hydration. And then there's type 4, which is low heat of hydration, so longer working time. And then a whole high sulfate resistant cement used in areas where there's a lot of sulfates, like in sewer systems. There's other types of cements, and they're pre-blended cements. Microsil anchoring cement is regular type 2 Portland cement with a little bit of aluminum powder for an expansion, and a lot of times they'll use silica fume and fly ash. But these are all pre-blended into the bags, ready to go. The results of the actual micro cement are high early strength, thixotropics, so it doesn't wash out, and dimensional stability, so it doesn't shrink or expand much. Cement is usually delivered in either 94 or 47-pound bags, or it comes in large super sacks. And more commonly, recently, with the addition of the silicate rules, we're seeing a lot of either the super sacks or cement in silos that's used to feed our batching equipment. So once we have the cement, the other ingredient is water, and the water needs to be clean, potable water. No organic particles in the water, so no river water, no lake water. Make sure that it is clean, potable water, and ensure you have enough water for not only the batching of the grouting, but cleaning up afterward. The next thing is the water to cement ratios. So we can mix the water and cement in different ratios to achieve different strengths. A very common water to cement ratio is 94 pounds of cement to 5 gallons of water, which will give us a water to cement ratio of 0.44. And then we also show some of the metric units. When we do mix this up, one of the main quality control tests is the specific gravity, which is measured with a mud balance. And for the 94 pounds of cement with 5 gallons of water, the typical mud balance reading, specific gravity reading, will be 1.8. So in our hollow bar grouting, we have two different types of grout mixes we're going to use. We're going to use a flushing grout while we're drilling, and then when we're done drilling, we're going to pump out all the flushing grout with a structural grout. So the flushing grout is usually a water cement ratio of 0.8, which would be 3 bags of cement to about 27 gallons of water, which would yield about 38 gallons total volume of cement slurry. And that's what we'll mix up to use for our drilling while we're drilling. Then the other mix that we use in hollow bar grouting is the final mix, which is the structural grout, which has that water to cement ratio of 0.45, which is typically about five bags of cement to about 25 gallons of water. The measures for once you're done with your batch, you need to measure the specific gravity of the grout, which will tell whether we've mixed the ingredients up in the right proportions. And the mud balance is basically you would take a small sample and put it on the scale, and it'll actually weigh it out and tell you the density of the grout. We're looking for 1.8 specific gravity plus or minus about 0.02. Another quick and easy measure is the flow cone test, which measures the viscosity of the grout, which is another way to determine the proportions of the grout in there. But it's not as accurate as the mud balance. So you can do the flow cone test temporarily to get a quick and dirty number, but you really need to do the specific gravity test with the mud balance to get the accuracy. A lot of the projects will require grout cubes to prove that the grout is not only mixed up in the right proportions, but the cement was not old, So they'll actually take samples with these grout cubes, and you'll set them aside, and you'll do a compressive strength test at different days during the life of that sample. So typically they'll do a break at 3 days, 7 days, 14 days, and finally one at 28 days. And that's just a final check because it's too late to change anything on the job site. The grout, cement and water gains strength during its hydration process, and it takes quite a while to fully hydrate the cement. So at day 1, you'll have about 45% of the total strength that you're going to gain. At day 7, you'll have about 75%, and at day 28, the day that most of the cubes are actually done for the final test, you'll have about 90% of the overall strength, of the compressive strength of the grout. And just a little note here that adding a little bit of water really changes the grout strength properties. So a 25% increase in water will decrease your grout strength by 50%. Quality control is important on the job site, so you are going to have to report and record a lot of the conditions on the job site. So you're going to have to record what type of material you're drilling through and the condition of that material. You need to measure the grout pressure that you're pumping with to try to get an estimation of the body of grout that you'll have around the anchor. You're going to want to measure the total volume of cement that you injected into the anchor, and then you're going to have to do a test after you've flushed out all the flushing grout and are pumping in the structural grout. You're going to need to do a little sample at the top of the hole to assure that the structural grout is getting all the way back up to the top of the hole. One of the ways you can measure the amount of grout is to measure the flow rate, or I mean the stroke count of the pump that you're using, or use a mag flow meter to record the total volume that you injected in there. And then finally you'll do the water to cement ratio based on the mud balance, which will give you your final specific gravity number. So once we have our grout mixed up, let's talk about the equipment and actually installing this material. So ChemGrout makes several different types of mixers and pumps for the grouting of anchors. We have a combination of piston pumps, plunger pumps. We have mixing systems of colloidal mixing and shear disc mixing. And then we offer those in several different power options, whether it's electric or diesel or gas or compressed air powered units. One of the main pumps we use for grouting anchors is our double-acting high-pressure plunger pump. The plunger pump is used because it delivers very high pressure. It delivers a known volume based on the plunger volume, and it's available in variable speed, so you can speed up and slow down the pump. We use our plunger pumps because piston pumps have a very high wear cycle on the piston pumps, and the plungers last a lot longer. We have a couple different types of mixing systems we offer for making colloidal grout. When you're doing hollow bar anchors, you need to have a high shear colloidal type mixer so that you have adequate wetting out of each individual cement particle. There's two ways that we achieve that. One is with what we call a shear disc, which is a high-speed disc rotating at about 3,000 RPMs in the bottom of the mixing tank, and it shears up all the different cement particles. And then we also offer colloidal shear mill pumps, which is a centrifugal style close tolerance pump that offers a high shear into the material. Both of them will achieve a colloidal mixed grout. The shear disc takes a little bit longer than the colloidal mixed pump, which is much more efficient. One of the primary units used for grouting hollow bar anchors is our CG680 high pressure unit. This would be used on large projects where you're doing a lot of anchors. This pump will do 32 gallons a minute. Well, the normal pressure is about 1500 psi, and this one is one of the units that has the high-speed colloidal mix pump, and then it has an agitator tank, and then it can be powered either electric or diesel. And the controls on the pump allow you to vary the flow rate and the maximum pressure that you're putting into the hollow bar anchor. We also have a shear disc model, which is used for smaller projects. It has the advantage of having two separate mixing tanks so that you can have flushing grout and structural grout mixing at the same time. This pump we set up at about 2000 psi to deliver that amount of pressure into the bit to create a bigger grout bulb around the anchor. The high pressure plunger pump is a very simple pump, very easy to clean. This unit is available either air powered or hydraulic, and the hydraulics can be powered by a diesel engine or by an electric motor. Some of the instrumentation that we like to use. So to measure the volume of grout you're actually putting into each anchor, you can use a magnetic flow meter. A magnetic flow meter is non-obtrusive, and the material goes right through the sensor area, and you can measure the flow rate, and you can measure totals, and there are two totalizers, so you can get the total for each hole, and you can also get the total for the entire day. The other instrument is a pressure gauge, which lets the operator know how much pressure is going into the hollow bar anchor. And if you see pressure rising, you can see if the bit may be getting plugged up with clay or debris that are stuck in there. So between the two of them, it's a good indication of what's going on at the end of the drill bit. For some projects that require recording, we have a monitoring system, which is a data collector, which takes the data directly from the mag flow meter and from the pressure transducer, and you can get a pumping profile of flow rate versus pressure for each individual anchor. And on the actual recorder, you can give it a hole number or an anchor number. And so at the end of the day, you have a full record of how much grout went into each anchor and what the pressure and flow rate was during the injection. We'll move on now from to the operator side of things. So one of the most important things we can do when grouting is have a trained operator and keep that operator with the machine. The operator should be responsible for not only operating the equipment, but cleanliness of the equipment and minor maintenance, such as greasing the seals. If with a highly trained operator stays with the machine, this will reduce your overall costs of repair and maintenance, and we should have a backup operator available in case our primary guy is sick for the day. When staging, before you're actually grouting, you want to stage the machine in a central location so that you can just move the hose around and keep the machine in the same place. You want to have sufficient room to store your cement materials and keeping the materials out of the sun if it's a hot sunny day. The mixer and pump need to be on a nice level location, especially if you're using a water batcher where you're trying to measure the water. And the material should be set, or the equipment should be set off the ground a little bit so that it's not in the mud, or so up on some pallets, and right next to that you should have some pallets for the cement to be there and for the operator, and also a couple of pallets for the empty bags. In environmentally sensitive areas, you may have to put a tarp underneath the grout plant, and build a dike up around the tarp so that you can catch anything from getting in out of the tarp and into the job site area. One of the things you want to do before you begin grouting is you want to make sure the machine's nice and clean. You want to grease all the grease fittings and add oil to the air motor lubricators. A good way to keep the machine clean is to spray some biodegradable oil or some PAM cooking spray on the outside of the machine. That way, when you go to clean it off, it won't be stuck to the machine. You want to check the engine oil and top off the fuel tank. Make sure you have fuel for the day. Check the oil level in the hydraulic tank and check the filter indicator to make sure that you haven't overpressurized anything. And then before you begin mixing, you want to check the insides of the mixers and the holder tanks. Make sure that they're clean, no foreign debris, and everything's all washed out. And then last, you want to make sure that you have a sufficient supply of water to be able to grout all day and have enough water to clean up at the end of the day. When you're starting up the grouting operation, you have to keep ahead of the drill. So the first thing before they start drilling, you want to make sure that you have sufficient flushing grout mixed up in both tanks. And so when drilling starts, you have enough material to keep them drilling. If you do happen to run out of grout during drilling, you need to stop drilling until you have enough grout made up. So the grouting is important that they keep ahead of the drilling operation. If you don't have grout, the drill bit will plug up and you'll have to pull out the entire string and put a new drill bit on, and possibly losing the hole. The other thing is if you don't have any grout and you leave the pump out, you can actually pump air down into the anchor, compromising the bond and corrosion protection on the hollow bar anchor. You need to be able to flip over to straight water. So there's a valve on the bottom of the tank where you can add water directly to the pump. So if you happen to encounter a boulder, you don't want to be drilling with flushing grout or cement at all. Cement's a poor lubricant and it may heat up really quick and flash set in the bit. So when you get to a boulder, you need to flip over to water. The water can act as a coolant until you get through the boulder, and then immediately after you're done, switch back to the flushing grout, drill through the rock, and then when you get to the final depth, you want to switch over to the final grout and grout it all the way back to the surface, measuring the density at the top with the mud balance. At the end of the day, the cleanup is very important. If you want the next day to go really good, tonight's cleanup is important. So run clean water through the entire mixing and pumping system all the way through the hose. Use sponge balls to clean out any scale that happens to build up on the inside of the hose. And then use a pressure washer to clean the inside of the mixer, the holding tank, and the outside of the machine. Then after you're done cleaning up, you want to turn everything off for safety, but you want to check the pump body, you want to check the suction and pressure valves for any grout deposit that built up during the day, and then use a hand brush to remove any of the grout stuck on the outside of the tank and in the inside of the mixing tanks. And then after you're all done, you want to make sure that you leave all of the valves open and the slide gates open so that if it happens to rain overnight, you won't get a collection of water in the mixing tanks. And especially in the wintertime when the water could freeze inside there and damage either the pump or the mixing systems. Lastly, we'll talk about operator safety training. Some of the protective equipment that is common for the grouting operators is gloves to keep the cement off their hand, rain gear or a Tyvek suit to keep the cement powder and the mixed grout off your clothes and skin. Safety glasses and a dust mask are required. Cement is good to protect steel, but it's corrosive to the skin and it can cause chemical alkaline burns. It's important that you supervise new workers, stay with them, train them on all the different procedures that need to be done, and don't just put the guy on the machine and tell him to go to work. Somebody's got to actually train them on what are the procedures, what are the mixing ratios. They need to remember that grout needs to be flushed off their skin immediately. If left on for a period of time, 3 to 5 minutes, it can start to cause third-degree burns on your skin. So it's important to either have gloves on, and if you don't have gloves, and if you happen to get some on your skin, just to rinse it off immediately. It's very important before you do your cleaning and maintenance work to make sure that you've shut down the equipment and locked it out, so that and de-energize any potential either compressed air or hydraulic pressure, so that it's safe when you're going in there to do the cleanup and maintenance. Please never stick your hand into a moving mixer or a running paddle. There's safety stickers on the machine to warn you, but please don't stick your hand into the mixer. And please prevent tools from falling into the mixer tank. Make sure nothing can fall in from above, and maybe tie a string onto your cutting knife and tie it to the machine so it cannot fall into the mixing tank.
All right, well, at this point, I'm going to take it over, but before I move on to some more safety, I just wanted to say if you know you guys have any specific needs and want to work with us and ChemGrout, we're able to distribute and supply you with the equipment that would work best for you. So feel free to reach out to Intech or Joe at ChemGrout to figure out what you want. All right, so then I'm going to move on to a little bit more safety. I think that that was a good background on what grout is and what it takes to effectively and efficiently use it on a site. So now I'm going to go through a little bit more safety as it relates to our elements and things to look out for. So alongside with the keys with cement that Joe outlined for safety, I just wanted to touch on with any construction project, and especially including installation of hollow bar and helical anchors, there's a couple other things to look out for. So there will be equipment moving around on a job site. It'll have overhead components because it's dangling things in the air. So it's always important to be paying attention to where things are moving, where you're staging things, making sure you're wearing a hard hat, making sure you have ear protection, high vis on, just the general PPE that you should be wearing. So then with, grout dust, silica, you should be protecting your eyes, nose, skin, ears. There will be loud noises. Just make sure that you're conscious of what you're doing and what could potentially impact you. Also, with the bars that you're putting on and screwing together, there's pinch points and bare steel. So make sure you're wearing gloves and make sure you're not, mishandling things because certain things can be sharp. So also when you're torquing, the screws and imparting stresses and hammering, there's a lot of force going on. So you don't want to be resting your arm on something and get jarred or get hit with something. So especially with it currently being summer, another thing that some people don't think about all the time is don't overwork yourself. You can't continue to do work if you're fighting heat exhaustion. Make sure that you're taking breaks when you should be and maintaining hydration. A thought experiment that I always like to do is trying to get yourself into a third person. What would you do if you were watching yourself work, or what would happen if your spouse walked by, or a family member, a friend, a coworker? Would they think that what you're doing currently is safe? That task that you're doing, are you doing it safely? So with this constant mindset, it kind of takes you out of the moment of, oh man, this is really tough. I need to get this done and rough it in there sort of mentality. And it can also help you kind of take a second, take the emotion out of it, and get a new perspective. And maybe you'll look at it and say, oh man, I could have been doing this a totally different way and it would have been way easier. So having that mentality will help you get home safe every day. and that is the most important thing. Make sure that you and all your coworkers and employees are getting home safe every day. So that's my safety soapbox, and now I'm going to get on to the really exciting stuff. So I'm going to start out with each type of element and discuss the individual components of each element and their installation. Then I'm going to go into the engineering design principles behind them. So I'm going to start out with helical pull-down micropiles. And before I really get into the helical pull-downs, I kind of wanted to start with a quick refresher on helicals themselves. So basically, a helical anchor is just a large steel screw that we use to torque into the ground until we find something stiff enough to get capacity. So just like a screw, the element consists of a shaft with some flights welded onto it. And when we transmit torque from a drive head, kind of like a drill, into the shaft, it turns the flights. The flights then screw into the soils and engage the soils until a specific torque or depth is met. And it follows that the harder you have to screw the pile into the ground, the more capacity you get out of the pile. And once you get to the end of your element, we finish that pile with a plate termination that gets cast into a footing. So generally, we kind of have two flavors of bare steel element, the square shaft and the round shaft. And the square shaft is a solid square shaft that ranges in square dimension from 1.25 to 2.25 inches. And these shafts are generally our most economical option because they have a high relationship between the torque and the capacity, and they're generally less expensive. So our second flavor of bare steel element is round shaft. And these are a hollow steel section of structural tube that range in dimension from 2.875 inches outside diameter to greater than 4.5 inches outside diameter. And these types of shafts are advantageous due to their ability to resist lateral loads, and they have a better unbraced length strength. However, these round shafts are slightly more expensive, so for the most part, we only try to select them when we have concerns for lateral stability, a relatively thick, weak soil down in the profile, or a weak soil that's near the surface of the profile. So throughout the years, Chance has these two, square shaft and round shaft, but they developed this solution where you can utilize square shaft materials with a grout column. And this is the helical pull-down micropile. This element can help alleviate those problems with lateral loads and weaker layers, while also adding the ability to take some of the required loading on in skin friction, which I'll talk about in a second. And that element, together is the helical pull-down micropile. So here are the kind of overarching concepts behind the helical pull-down micropile. For the most part, the helical pull-down is really just comprised of a helical anchor with a grout column annulus that is gravity pulled down as the helical is advanced. So one big benefit to having both the helical lead section as well as the grout column is you get to develop both the end bearing and the plates as well as the skin friction as you go down. So when any element is loaded, the load is first taken in skin friction until the whole element strains enough to engage the tip. So by doing this, we're able to take a load like 100 kips and resolve it into 70 kips of friction resistance and have the remaining 30 kips be taken down to the helical flights. And this allows us to choose much less steel than before, which helps make up for the increased cost of grout and labor. So these elements can theoretically be reduced in length by getting more of that friction than before. Additionally, these elements have the option to be either left uncased, so where the soil is the outside diameter, or cased for the upper depths is what we typically see. And if casing is used, it can really be used to bolster the lateral resistance of the pile section. So here's a list of the major components for the helical pull-down. These sections are literally just the same components for a typical traditional helical pier. So you have your termination, you have your extension sections, and you have your lead section. The only difference for the helical pull-down micropile is you add to it the lead displacement plate, the extension displacement plate, and then you have your grout body. So for the uncased pile, the size of the lead and the extension displacement plates will dictate the design section of the element that is installed. For a cased pile, we typically use the size of the smaller extension plates that'll go through the casing, but it'll be dependent on your specific pile design. So here's a closer look at the lead and extension displacement plates. You can see on the bottom right, the lead plate is a round steel plate that slips over the bar, and it has two paddles that displace the soils as the bar is turned. Then at the top right, you can see that the extension displacement plate is that same round steel plate that slips over the bar, but it doesn't have the paddles. So these are put at each extension section that is added to the bar during installation, to where when you get the bar sticking up out of the ground, you add one of these, then you add your extension. And I think there'll be a graphic representation, a visual representation of that in a moment. So here's the cased version of these same components. And the primary difference is that steel collar that is welded onto the round plates. And these serve to slip onto the casing sections and hold it in place as the elements are installed. So then the same thing happens. The bars torque the round plates, which turns the paddles and displaces the soils with the lead displacement plate, and then maintains the hole diameter during install with the extension. So for those of you who are more visually inclined, I think this should give a good idea of what it looks like to install a helical pull-down micropile. And this is my first example. I'm going to show an uncased installation, and it'll include a grout column for all the extensions. First, you set up and install your lead section, and you do this by applying crowd with your equipment and applying torque with your drive head. So you're pushing down and screwing the lead section into the ground. You're not drilling. You don't want a bunch of spoils to come up out of your hole. You just want to move the soils out of the way slightly. And you do this until there's a little bit of stick up out of the ground. After that, you add your lead displacement plate, the one with the paddles, and then you add your extension. And you also want to set up a grout reservoir that'll hold grout during your installation. We usually see this being done with just a sonotube, and it needs to hold enough grout to where you're not constantly filling it, but not big enough to where you spill out excess grout at the end of the element whenever you take it away. So another note is you're probably going to have to bury the reservoir a little bit or seal it around the bottom so grout doesn't come out. So you fill your grout reservoir, and then the next step is going to be advancing your element, applying more crowd and torque. The extension displacement plates and extensions should be added as necessary as the configuration penetrates the ground. So you can see you've advanced it a little bit. The lead plate is digging into the ground, starting a column, and you're just maintaining grout and adding extension and extensions plates as you go. So like I said, creates grout, lead plate creates an annulus. So keep doing the same thing, applying torque and crowd, add your extension plates and extensions as necessary, and you maintain your annulus, and your lead plate creates even more of a column as you go down. And then once you achieve your depth and torque, you can cut off excess shaft and terminate it with a pile cap. So one thing that's important to note on these elements, as they're both frictional and end-bearing elements, it may be necessary to double check that the installed pile meets your design criteria. And what I mean by this is if you torque up early, it may mean you have less frictional resistance that you planned on for your design. So you just have to check that the combination of the steel helical, the leads, can take on the remaining load, and that the soils can calculate out to take the loads as well. So if you're doing an initial design or installation of one of these, you run into this and you're worried about it, just reach out to us and we can help troubleshoot it with you and help come up with a solution to get it to work. So at this point, the foundation contractor will cast the termination into the footing. It's important for design to look to have the cap in a spot that doesn't interfere with the other reinforcing in the pile cap. That'll ultimately be on the structural engineer of record for the footings though. So here's the completed element with each of the components that we discussed. Now I'll go into our second example of installation, but this time it'll be for a cased element. And so the installation is mostly the same, but there's a way that we'll handle the grout and extensions that'll be slightly different at the beginning of the install. And I want to note that you can fully case your element, but we find that that's relatively uncommon. What is more common is to install casing in the upper 7 feet or so for lateral resistance. So with this method, we'll install casing in the upper portion of the pile and leave that casing up top while we continue our pile down, just so that we can resist that lateral load within the range that the moment has to resolve. So just as before, we start by advancing the lead section. We apply crowd and torque until the element is mostly into the ground. At this point, you'll add your cased lead displacement plate, extension, and casing. Before you advance the pile, add your extension displacement plate, then you slip your drive head over the shaft. And you want to kind of sandwich the casing between the extension displacement plate and the lead plate. And you want to do this in a way that it keeps them together, but you're not pushing the system into the ground. You're just keeping them tight, and the lead flights should pull everything down while the drive head keeps them sandwiched together. So with that, you pull your amount of casing into the ground, but not far enough to where you can't retrieve your extension displacement or your extension plate. So at this point, remove your cased extension plate and install a grout reservoir. Fill the grout reservoir and add extension plates and extensions as necessary to achieve more depth. And so note that for these elements, you switch over to a specifically sized extension plate that fits inside the diameter of the casing. So typically for design, the lead displacement plate is slightly larger than these extension plates, so we slightly reduce the pile diameter to the smaller extension plate diameter or somewhere in between. So you repeat this process, adding more length of pile with the extension plates being slightly smaller and passing through the casing as you go. And you keep, creating that annulus as you go with depth so you can have a relatively long micropile section that isn't limited. Once you get to your torque and depth, you can cut off your pile. And like I discussed earlier, make sure you pay attention to both the length and torque on these. Since they are both frictional and end bearing, you might have to make some adjustments during construction to make sure the installed pile meets the requirements for the project. Now you've taken away the reservoir, you cut off the shaft, and then you just fit a pile cap on top and bolt it if necessary, and that's it. Now the termination gets cast into the footing and you're done. So here's a representation of a completed, partially cased helical pull-down micropile. So here's a couple pros and cons for the helical pull-down micropile and when to use it. So like discussed before, you can use less steel section by carrying more load in the grout and friction. The torque should be monitored during installation, and we can go back, figure the strength of those materials we penetrated to double check calculations so you get confirmation. You get an increase in capacity carried from the skin friction and also get additional strength in end bearing, which is good, especially if you don't have something really hard. If you have a marginal soil or stiff, you can get some of that end bearing. You can advance casing with one piece of equipment. You don't have to go in and install it beforehand. You can pull it down with your element, and it's a good one pass with a gravity-fed grout annulus installation method. So it helps keep the hole open during installation. You don't have to, put in and withdraw casing as you install. So some of the cons include, the grout needs to set up before testing, load testing. This can be alleviated through admixtures or starting with a higher strength grout and confirming your grout with brakes. But that's just something you have to watch out for. And then also you can't penetrate into rock sufficiently to create a rock socket. You can get the tip to seat into the rock a little bit and count on the structure, the shaft to structurally transmit the forces, but you can't fully get a rock socket in. So the design principles and engineering information in the Chance Tech Manual is really useful. So if you don't have access to it or you don't have access to the current edition, feel free to reach out to us and we can help you get set up with a copy. I've also included a snapshot of the different square shaft ultimate capacities as well as the torque ratings. But like I said before, if you're doing a helical pull down, we can achieve a much higher capacity with a combination helical micropile than just the helical itself. So these loads are just the starting point. So I can also get you access to Helicap, which is the software that Chance came up with that lets you input the soil profile, estimate what bar size and grout column you need to achieve a specific pile capacity, And there's also some tutorials on the Chance website that do walkthroughs of how to use the software. So feel free to contact us to get access to that. But I think if you search Helicap and Chance, it should pull up and be pretty easy to get signed up. So now I'm going to discuss hollow bar micropiles, including the components and then the installation. So this image represents the different components for a completed hollow bar micropile. The first set of items that I've highlighted here are the hex nuts and termination, final injection grout, couplers, and sacrificial bits. So the hex nuts are just like the termination on the other pile. It gets cast into the footing at the end and transmits the forces from the footing into the bar, just like the other. So second I have is the final injection or structural grout. This is going to be pumped through the element at the end of installation, and it displaces the flushing grout that was used during drilling. Third is the coupler, and that's going to attach the different sections of the threaded bar together to add length as you drill. And then finally, we have the sacrificial bit with holes, ports that cut into the soil profile to create the annulus. Typically, we use the diameter of these bits in design for the diameter of the grout column, which is actually conservative because we're going to be slightly pressurized grouting these, and it'll tear away at the walls of the column, so it'll be conservative. So this next image highlights include the soil cement grout body, the drilling bar itself, the centralizers, which are optional. So the grout body is the thinner grout initially that permeates the soils, especially if they're highly permeable during installation. So we're under pressure, and that grout body, as we're advancing our drill string, it's going to leach into the soil a little bit. So it's going to have a much better connection with the structural grout at the end of the project than the soils would by design themselves. So we don't typically design with this in mind, and it helps us overperform for what our design says. So second, we have the MagnaCore self-drilling anchor bars. These are threaded hollow tubes that transmit the forces during drilling. All of this is also sacrificial, so it acts as the pile reinforcing during the design life of the project. We have both rope threaded and trapezoidal threaded bar, and it ranges in diameter from about 32 millimeters on our thinner line up to 103 millimeters for our heavier bar. And then finally, you can add centralizers, which are important if you need to hold the reinforcing towards the middle of the hole. And this is especially important in horizontal drilling applications. So I discussed bits earlier, but wanted to go a little more in depth. So we have different bit sizes ranging from a few inches up to 8 or more inches, which makes the diameters of the holes we use for design. Feel free to reach out to us if you have a specific combination you want to use, and we'll see if it works out well or if we have to get around it in any way. So first, I'm going to discuss the clay bit at the bottom right. This is ideal for mixed fills and softer clays. So if you have a relatively clean profile with no real dense or hard spots, we can get away with using that one, but it's a little risky. The second one is the middle one, is the crosscut bit. This is pretty common bit that we use. You're able to get through denser and stiffer profiles, and you can even get a rock socket several feet into somewhat competent rock. But if you have hard rock, or if you're planning to go pretty long into rock for capacity, at a certain point it just becomes more efficient to use the button bit. You'll spend too much time with the crosscut bit than you would if you would just switch over to a button bit. A button bit has the little buttons on it that tear and pulverize the rock, and it goes a lot more quickly into competent rock. So like I mentioned before, each of the bits have grout ports. So when we install these anchors, the grout goes into the drill, through the bar, through the couplers, and then finally through the ports at the bottom of the bit. So with this method of installation, whenever the drill is being advanced, like Joe kind of mentioned before, there should always be grout flowing through the system. So grout should flow all the way down to the bottom and out the tip. And always start pumping grout first as you advance the drill string. So the following slides are going to be a graphic representation, just like before, of how these get installed. You start with your lead section to the location you want to install your pile. You attach this section to the drill string, start pumping grout, then you start drilling. So you advance your lead section with grout pumping, And then at this point, we'll be using flushing grout, and it'll be at a relatively thinner mix than your final grout, if they allow it on your job. So once the top of your lead section is a little bit above the ground surface, you disconnect it from the drill, add a coupler in your next bar extension, and then reconnect everything to the drill, and you keep drilling. It's important to note that the drills have a hammering action. This isn't always needed, but when you hit a dense layer, you can hammer through, similar to how like an impact drill works. It'll add a hammering action. So it'll help advance through those dense zones or tear through boulders, and it'll help later when creating a rock socket as well. So as you can see, you know, you hammer through the dense layer while you also apply your crowd and torque. Advance your system, pumping flushing grout always while drilling. Repeat the steps until you get to your design depth. You know, so you're just crowd torque drilling. So now you can see I've added a darker section of grout. You're going to pump that structural grout through your system and displace all of the flushing grout until it comes out of the top of your hole. So notice that the flushing grout still remains, and it's permeated into the soils, and it creates a better condition than we count on for design, because we only count on that diameter of the structural grout that's shown on this page, which is about the size of your bit. At this point, terminate with the plates and nuts as the design requires, and then cast your termination into the footing. One other note is, you know, for these elements, you can utilize casing. Currently, typically when we see this happen, you go out, or somebody goes out and they install the casing to the depths that you want at the locations, and then you just install your hollow bar micropile through the middle of that. Pros and cons for this: hollow bar falls under the design guidelines put forth by both the FHWA, PTI, and a bunch of others. So it's established, very well established. With hollow bar, you can create a column even into dense profiles and rock, several feet to, you know, a lot of foot of rock for a good rock socket with a button bit. When permeating grout into the soil profile, we're going to have that better bond strength. So we're kind of improving the soils. We'll typically overperform relative to our design. And then with it being a one-pass installation method with constant grout, you know, we won't have that problem with hole collapse while you're installing. So it's a good alternative to conventional micropiles that require a cased method of installation, you know, where you have to put in and withdraw your casing. That labor adds up, and our one-step method really is competitive with that. So the cons, similar to before, you know, the grout needs to cure before you can test. You can use your admixtures or use a higher strength grout if you need to do something fast. There's also no quantifiable feedback of what was encountered from a strength standpoint. So you don't have a measurement of torque like we did before. But you can tell if you're getting into something dense and you have to hammer through it, or once you hit rock, it's definitely pretty obvious. So here's some of our engineering data inputs for design. Like I kind of talked about, we have both the rope, which is the R series, and the trapezoidal threaded bar, which is the T series. So the naming convention is the thread style, and you have R or T. Then you have the outside diameter in millimeters. So the R32 is a rope style 32 millimeter, and then we have a couple different wall thickness options. So as discussed earlier, the two types of bar, you know, we have that they don't fit with each other. So if you have one system that carries a T style or an R style itself, they won't fit together. But we have adapters, and we can help you get something that'll fit for your equipment, or we can help you adapt over to another bar style. So we're at the home stretch. I'm going to try and go through this pretty quickly because we are at our 55 minutes right now. So I'm going to go through these structural checks and geotechnical design checks, but I just want to kind of preface it. You know, this presentation is topical. It's just meant for you to get an idea of what's going on, so that when you read through the design methodology, that you kind of have an idea of what it looks like and what you should be considering. So don't use this as a basis for your design. Just use it as your initial look through of the design methodology so you can get oriented. So the first point for structural design is the structural checks, and what is required for your design methodology. So every project is going to have a design methodology called out for it, or if you're choosing, you should choose a design methodology to follow so that everybody can design to the same thing. So the main concept we're digesting on a project is we're given a design load. How much steel and concrete do we need? How strong of a section to carry the loads down structurally? So we generally use the same design methodology checks for both the helical pull-down micropiles and hollow bar, making sure that those pressures don't exceed the strengths of the grout and the steel. But for the most part, the helical pull-down steel sections are pretty solid compared to the hollow bar sections, and those typically control through torque, so it usually doesn't have a large effect on our design for the helical pull-downs. So we check these elements depending on if the element is going to be loaded in compression or tension or both. And the two equations shown are the checks we use to determine if we have enough strength to carry the loads. So the top equation is the allowable compression capacity of a pile section. With that, we check the allowable load on the grout column, which is related to the size grout column, and then the steel capacity. And then the bottom equation is what we check against the planned tension load, and this only includes the strength of the steel. So this is just a blown up slide that shows the individual terms of each of those equations. There's a few variables that are represented here. Please use the correct factor of safety and the correct FY, the yield strength of the bar in their respective places as the specific design methodologies require. And as I mentioned before, we have different factors of safety for the grout. We have a different factor of safety for the steel and compression and for the steel and tension. So especially with how these are laid out, pay special attention and use the right factor of safety in the right spot. Also, as engineers, what are the factors of safety for? Consider things like how is the grout mix? How well did everyone follow the mix design? How fresh was the cement? And for the steel, how is it manufactured, stored, and handled? And we just want to include some sort of buffer that takes care of these things, make sure that what's in there will not have any problems. And the design methodologies have the recommended safety factors to use, and they have what FY bar you should use relative to whatever testing you have. So like I said before, use the right safety factor. They're different per each term. And then for the steel strength, it needs to be the minimum of the what is the comparison for the grout and steel, which is that top equation, the modulus of the grout or steel times 0.003. And that's because if you strained too far, the grout would fail by then. So you got to limit it to that. Or if your bar is has a lower yield strength than that, then you use that lower strength. So the way that I like to think about the strain compatibility of a grout and a steel element is it's strain compatibility. If you had two springs attached to a block and one was fat and one was skinny, and you push down on everything and everything was held uniformly to where the block had to move down the same, how would each spring act? And the answer is, the fat spring would have to take on more of the load and the skinny spring would have to do less, because that's how the stress and strain works. And in this case, in compression, the grout's going to be the fat spring. As it does very well in compression, it'll take on more of the stress. You won't be relying on as much of the steel. And then in tension, you'll be counting on the grout as well, but the steel will perform much better. So we check these two things on each of the designs. We check the design strength with the design load, and we check the test strength with the test load. And basically, we use a reduction on the design strength of the pile, which adds conservatism. Then we also reduce the strength of the bar for the comparison with the test load, but we don't reduce it as much as it only has to perform during that test. So another thing we account for in designs is lateral load. For the most part, when lateral loads are more than a few kips, the pile section will likely need to be cased to achieve enough capacity to support them. So when we do our design, we're using all pile. We add a design section, analyze it, and check to see what the deflection and max moments are. And then at that point, if the deflection is within the tolerance of the project, we move on to checking the flexural strength of the pile. If not, we beef up the section, add casing if necessary, and repeat until we have a passing section. So now I'll move on to the geotechnical design. For the hollow bar elements, they're predominantly frictional. If you get into some rock, some competent rock, you can count on some end bearing, but for the most part, they're frictional. And then the helical pull-down micropiles is both a combination of that frictional component and also the remaining loads at the bottom go into the helical flights and end bearing. So each of them, as we discussed, has options to resist lateral loads with casing or just the grout steel section alone. So for skin friction, we're creating a long, slender grout tube that will have contact with the ground. That tube has a surface area given by pi times the diameter times its length. This area in conjunction with the bond strengths will give you an overall resistance to downward and upward forces. We typically use to look published values for initial design. FHWA has some values that we typically look at, but you can always check it during construction with a load test, or if you have some specific experience with the site, you can use that. It's important to not count on soils in fill areas, unbonded or free stress lengths or zones like that. So if you have more capacity outside of these zones, then during your design life, you'll have more capacity. Second thing is the end bearing. For the most part, this equation is going to be more related to the helical pull-down micropiles. The flights at the helical section will distribute the load into pressure into the soils. The Chance Technical Design Manual goes into this a lot more in depth and is a good reference. So I think you should use that for a lot more detail. And make sure that you're using the correct bearing capacity factors for your soil and use your engineering judgment. Lateral loads from a geotechnical standpoint, it's important to understand, the upper depths of the soils, within the first 10 feet are the ones that are going to be loaded, and that's where your moments are going to be resolved. So it's really important that if you have a lateral load planned on a project, that we get a lot better resolution of testing and higher quality testing at those locations. So blow counts are good, but shear testing is better.